Next, we discuss what the first-order necessary conditions for equality constraint problems mean geometrically. So here we considered an example of the problem of minimizing f of x subject to a single constraint h of x is equal to 0. On this figure, we see the feasible region is given by this ellipsoid here. So this is the set of points where h of x is equal to 0. Okay, so and then we also see the isocost lines for the function f. Okay, so this is the isocost line for f equal to c1, f equal to c2, f equal to c3, and f equal to c4. These are the level sets for f corresponding to the different levels, right? And also you can think of the feasible region as the level set for h corresponding to the level equal to 0. Now we know that geometrically the gradient is orthogonal to the corresponding level set, right? So we know that if we take an arbitrary point here, let's say in the level set that describes the feasible region, then the gradient must be orthogonal to the corresponding level set, so it points like this. And we also know that the gradient points in the direction of the function increase, right? For example, because h of x is equal to 0 for our feasible region, and we see that the gradients of h point to the outside, it means that outside of this ellipsoidal region, the value of h of x will be greater than 0. So outside h of x is greater than 0. And then inside of this ellipsoid, h of x will actually be less than 0. All right. So now, similarly, we can actually find out the order of values c1, c2, c3, and c4 given here. So if we look at where the gradient of f points, the gradient of f points in this direction, right? So it means that the function is increasing as we move in that direction. So therefore, we can see that c1 is less than c2, less than c3, and less than c4. Okay? So we can also see that if we keep increasing the value of c here, if let's say we increase the value for the level from c4 to something larger, then we would be outside of the feasible region, right? So therefore, as we move the isocost line for f higher and higher, this point x1 will be the last one we will touch in the feasible region. Therefore, x1 is actually a local maximizer. All right. So similar, if we go down and if we push the isocost line down, this will correspond to the decrease in the value of f. As we keep pushing it down, the last point that we touch in the feasible region is the point x2. So this point is the point of the minimizer, local and global, in fact, in this case, right? And if we look at the gradients at these 2 points, we can see that in both cases, the gradient of f and the gradient of h, they are parallel to each other. So in this case, they point in the same direction, and in this case, they point in the opposite direction. But in both cases, they are actually parallel to each other. And this is exactly what the first-order necessary condition predicts. It tells us that the gradient of f in x plus lambda times the gradient of h in x is 0. This means that the gradient of f in x is given by minus lambda times the gradient of h in x. This exactly tells us that, the 2 gradients are parallel to each other, so they can point in the same direction if lambda is negative, so they'll point in the opposite direction if lambda is positive here. But in both cases, they're parallel to each other. So if a point is minimizer or a maximizer, then they must be parallel to each other. And this is what we observe here. So if I take some other point, let's say if I take this point right here, so let this be x3. So then what's the gradient of f? The gradient of f is orthogonal to the level set corresponding to this point. So it points in this direction. What's the gradient of h in this point? It will be like this. Okay, so it's orthogonal to the feasible region. So we see that these 2 directions are not parallel. Therefore, the point x3 is not a candidate for a local minimizer or a maximizer. And of course, we can easily see that there are points with better objective in the close proximity of this point right here, and then there are points with the smaller objective in the close proximity of this point. So obviously the point x3 is not a minimizer or a maximizer for our problem.
I love it.